You know, we're literally surrounded by curves. Think about it. The arc of a ball you toss, the bend in a road, even the spiral of a seashell. But have you ever really stopped to think about the elegant, almost invisible geometry that's hiding inside every single one of them? Well, today we're going to pull back the curtain and uncover that hidden world.
It all kicks off with a really simple question, but man, the answer is surprisingly deep. How do you actually measure bendiness, right? How can you put a precise number on just how sharply something turns? It's definitely not as easy as just taking a ruler to a straight line.
Intuitively, we all get this. A hairpin turn on a racetrack has a really high curviness, right? While a long, sweeping highway on-ramp has a really low one. But when you get into mathematics and engineering, just having a gut feeling isn't good enough. We need a precise, universal way to describe this property. And that's what we call curvature. Okay, so here's our game plan. First, we're going to figure out how to define the bend. Then, I'll introduce you to this beautiful idea called the kissing circle. From there, we'll discover a curve's secret hidden path, learn how to unwrap it like a piece of string, and finally, we'll see why any of this actually matters in the real world. Let's do it.
All right, first things first. Let's get a solid handle on what exactly we're trying to measure here.
So curvature is the official term, and it's not some vague concept. It's a specific, concrete number that tells us exactly how much a curve is deviating from being a straight line at any single precise point along its path.
But what kind of tool could possibly measure the bend at a single, tiny, infinitesimal point? I mean, a ruler is totally useless here. We need something way more elegant, something that can perfectly match the curve's bend right at that spot.
And that brings us to what I think is one of the most beautiful and clever ideas in all of geometry, the kissing circle.
Yeah, it turns out the perfect tool to measure any curve is another curve. And not just any curve, but the most perfect, most uniform curve we know, a circle. A circle's bend is the same everywhere along its edge, which makes it the absolute perfect measuring stick for this job.
Now, the fancy name for this is the osculating circle. The word osculating actually comes from the Latin word for to kiss. And honestly, that's the perfect way to describe it. For any point on a curve, there's one and only one circle that just barely touches it, hugging its bend more snugly than any other circle could. It basically kisses the curve at that one spot, matching its direction and its bend perfectly.
And this is how we get our measurement. The radius of that kissing circle is what we call the radius of curvature. Now here's the key thing to get, and it's a little backwards. It's an inverse relationship. A really tight bend, meaning high curvature, gets a tiny kissing circle with a small radius. And a gentle, sweeping bend, which has low curvature, gets a huge kissing circle with a really large radius.
And of course, every circle has a center. Well, the center of our kissing circle is called the center of curvature. Now, I want you to hold on to that idea, because that one little point, it's about to show us something truly extraordinary.
So far, we've only been looking at a single point on our curve. But what happens when we start moving? When we look at the whole thing?
Just think about that for a second. As we slide along our main curve, that kissing circle is going to change, right? It'll get bigger and smaller, and as it does, its center point is going to move around. What kind of path do you think that center point would trace out?
The process itself is actually pretty simple to imagine. You just pick a point on your curve, you find its center of curvature, and you put a dot there. Then you scoot down the curve a little bit and do it again, and again, and again, all the way along the curve. And when you connect all of those dots, something amazing happens. You end up creating a completely new curve. And this new path, this collection of all the centers of curvature, has a name. It's called the evolute. It's like a beautiful ghost curve, or a hidden skeleton of the original, perfectly describing the journey of its bendiness.
Now for the really, really cool part. This amazing relationship isn't just a one-way street. We can actually work backwards.
So if the evolute is born from the original curve, it turns out you can also use the evolute to recreate the original curve. And the curve you get when you do this is called the involute.
This is the classic way to visualize it, and it just works perfectly. I want you to picture the evolute curve as a solid shape, like a cam. Now, imagine wrapping a string tightly all the way around it. Pin one end of the string down, and then just start unwrapping it. But you have to make sure you always keep the string pulled completely tight. The path that the very end of that string traces as it unwraps, that path is the involute.
So let's just put these two side by side to make it crystal clear. The evolute is the path made by all the centers of curvature. The involute is the path made by a string unwrapping from that evolute.
They're basically two sides of the exact same geometric coin. And here it is. This is the big punchline. The most crucial part is that they are perfect partners. If you take a curve and find its evolute, and then you treat that evolute as your new starting curve and find its involute, you get the exact same curve you started with in the first place. It's this beautiful, perfect, symmetrical relationship.
Okay, this is all incredibly elegant and kind of mind-bending, but you might be asking, is this just some neat mathematical party trick? And the answer is absolutely not. This hidden geometry is quietly shaping our entire modern world. For starters, take a look at the teeth on almost any gear you can find. They're almost always shaped like involutes. That specific curve is what lets them roll against each other perfectly, giving you a smooth, constant transfer of power without any slipping or jarring. Engineers use these exact same principles to design those smooth transitions for highway on-ramps and high-speed rail lines so they feel safe and comfortable. I mean, this hidden geometry is just everywhere, from computer graphics to physics, and even in the beautiful natural spirals of seashells.
So the next time you see a gear turning, or you're driving around a smooth bend in the road, or maybe even just pick up a seashell on the beach, I want you to remember that hidden dance of kissing circles, evolutes, and involutes that's happening just beneath the surface. It really makes you wonder, doesn't it? What other hidden geometries are just waiting out there to be discovered in the objects we see every single day?